Do you see it?
Yes.
Oh, okay. Let me check on YouTube. Okay, you are online.
Okay, thanks.
Thanks, Yahya. I need to jump to another meeting, but I will come back when I can.
Okay, sure.
Okay, bye.
Bye-bye. So I think we are online. Yes. So let's get started. First of all, sorry for the delay. Hello, my name is Yahya. Today I will be presenting our work U-TRR on uncovering the operation of the In-DRAM RowHammer protection mechanism. This paper published at Micro 2021. So let's start with a quick summary. First, RowHammer, as we all know, the RowHammer vulnerability of modern DRAM chips is a critical reliability and security issue, and DRAM vendors implement target row refresh to protect their DRAM chips against RowHammer. And however, target row refresh is an obscure, undocumented, and proprietary RowHammer mitigation technique. Due to its proprietary nature, their security guarantees are not proven and cannot be easily studied. So therefore, in this work, we try to answer these questions. Is TRR truthfully and secure, and how can we validate its security guarantees? So to this end, just 1 second. Okay. To this end, we proposed U-TRR, a new methodology that leverages data retention failures to uncover the inner workings of TRR and study its security. At a high level, U-TRR works in 2 steps. First, U-TRR profiles the retention time of a row R, and then finds when the TRR refreshes that certain row R to understand the underlying mechanism of TRR. And using U-TRR, we analyzed 45 DDR4 DRAM modules from 3 major DRAM vendors. And through this analysis, we make several observations. And with these observations, we crafted new RowHammer access patterns that will bypass the TRR mechanism and cause RowHammer bit failures. So our results show that first, all 45 modules we tested are vulnerable to RowHammer. Second, in many modules, almost all of the rows exhibit at least 1 row bit flip. And finally, our access pattern can cause up to 7 RowHammer bit flip in an 8-byte data word, making ACC ineffective. So we believe that U-TRR can enable more secure RowHammer protection mechanisms in the future. So this is the outline of my talk, and let's start with basic DRAM background. So here we see a typical system with a CPU and DRAM module that has several DRAM chips, and each chip has there are multiple banks in it, and these banks are organized as a 2-dimensional array of DRAM cells, and a DRAM cell stores a single bit of information as electrical charge. And in the bank, the cells are vertically connected to the sense amplifier, which can read or write the data from the cell. And also the cells are organized horizontally as DRAM rows. So to access the DRAM row, the memory controller first issue an activate command. And this activate command basically loads the DRAM rows data to the sense amplifier, where the data can be accessed with read or write commands. After that, memory controller must issue a precharge command to close the DRAM row so that another row can be opened later. So each DRAM cell encodes information in fundamentally leakage capacitors. Here's a simplified diagram of a DRAM cell. The data stored in the red capacitor, and the access transistor connects capacitor to the bit line. And there are multiple charge leakage paths and where charge can enter or exit unideally. The important thing to note that is that the stored data can be corrupted if too many charge leaks. So this is a simplified diagram of capacitor voltage over time, and we have a threshold called Vmin, which under which we can no longer guarantee that the data can be correctly read. As long as our voltage is above this Vmin threshold, we can correctly read the data of the cell, and we call this retention success. However, as soon as we go below this line, we consider this a retention failure, and we see basically a bit flip. In order to prevent these retention failures, periodic refresh operations are issued to recharge the capacitor voltage, and the time interval between the refresh commands basically called a refresh window. So let's look at RowHammer and the currently employed RowHammer protection mechanisms. So in order to access a DRAM row, let's say row 2, the memory controller issues an activation command to open the row. Then after serving all requests, it performs a precharge command. It issues a precharge command to close the row. And due to an increase in cell-to-cell interference as a result of increased packing density, the rapidly activating a row many times can cause bit flips in the nearby rows. And if we continue to access the row more times, even more bit flips can occur. And this phenomenon is known as RowHammer. And we refer to the rapidly activated access row as an aggressive row, and the rows containing bit flips as victim rows. So to protect their DRAM chips, DRAM manufacturers implement proprietary mitigation mechanisms known as target row refresh, or TRR. The key idea of TRR is to basically refresh nearby rows, victim rows, upon detecting a potential aggressor row. And let's look at how TRR operates at a high level. The TRR mechanism basically detects an aggressor as a result of repeatedly activating and precharging the same row. And after that, if TRR mechanism receives a refresh command, it piggybacks the TRR-induced refreshes to the aggressor, to the neighbor potential victim rows to refresh them, and thereby preventing RowHammer bit flips to occur. Although this is how TRR operates at a high level, with different vendors implement different TRR mechanisms, and we don't know their exact operation. Therefore, we cannot study their security properties and make sure they are fully secure. Therefore, in this work, we try to study in-DRAM TRR mechanisms to first understand how they operate, assess their security, and secure DRAM completely against RowHammer. So now I will be talking about our methodology for uncovering TRR method operations. We proposed U-TRR, a new methodology to uncover the inner workings of TRR mechanisms. The key idea of TRR is to use basically the data retention failures as a side channel to detect when a certain row is refreshed by a TRR mechanism. U-TRR consists of two main components, row scout and TRR analyzer. Row scout finds a set of DRAM rows that meet certain requirements as needed by TRR analyzer and identifies their data retention times of these rows. And the second part, TRR analyzer, uses these previous row scout provided rows to distinguish between TRR-induced and regular refreshes and builds an understanding of the underlying TRR mechanism. Let's look at these the parts in more detail. First, row scout. The goal of row scout is to identify a list of useful DRAM rows and their retention times. And RowScout must find first rows with consistent retention times. This is critical for U-TRR to correctly infer if a row has been refreshed by a TRR-induced refresh operation. And secondly, RowScout must also find multiple rows or row groups that are located at certain configurable distances and have the same retention time. And this is required so that U-TRR can observe whether or not a TRR mechanism can refresh multiple potential victim rows at the same time. Now I will explain the RowScout operation using a flowchart. So first, RowScout searches for DRAM rows that have retention time T. RowScout provides this retention time basically simply by initializing a row with a known data pattern, such as all ones, then it waits for T and checks for retention bit flips. If it has retention bit flips, then this means that the retention time of that row is basically T. And step 1 outputs address of this retention time T. Second, RowScout puts together rows that have certain row address lists among them, as indicated by the configuration parameter, what we call row group layout. Here is an example row group layout, which has 3 rows indicated by V, and they are one row apart from each other. And depending on how many rows are found in step 1 and how many of them can be combined to match this particular row group layout, step 2 outputs the candidate row groups, a set of candidate row groups. If the candidate row groups are fewer than needed, RowScout basically increases the T and goes back to step 1. Otherwise, RowScout need to make sure these candidate rows are consistent. And the RowScout basically runs the profiling retention time profiling operation multiple times to make sure that they are consistent, and it outputs the row groups. If the row groups are fewer than needed, again it will increase the T and goes back to step 1. Otherwise, it will output the row groups as retention profile rows. Now let's look at the second part, TRR analyzer. The goal of TRR analyzer is to use the RowScout provided rows to determine when a TRR refreshes a victim row. So at a high level, TRR analyzer runs a certain DRAM access pattern, and second, it analyzes, monitors retention failures in RowScout provided rows to determine when TRR refreshes any of these rows. And third, based on when and which of the RowScout provided rows are refreshed by the TRR mechanism, the user develops an understanding of the underlying TRR operation. Now let's look at a general TRR analyzer experiment. As the first step, TRR analyzer initializes retention profile rows with known data. It also initializes some aggressive rows. The user specifies aggressive rows in locations relative to the retention profile rows. For example, here we have a row group with 3 victims that are one row apart from each other. And the user can specify 1 or 2 aggressive rows between the victim rows. And hammering these aggressive rows will probably disturb the remaining 3 victim rows. Second, TRR analyzer performs a set of operations to reset the internal state of the TRR mechanism so that it isolates the actual experiment from the initialization and the previously performed experiments. After that, if TRR analyzer does not activate any of the victim rows for their profile retention time T, we expect to see retention bit failures when we read the data back and check for bit flips. So in order to make TRR perform a refresh, TRR-induced refresh operation, DRAM has to receive a refresh command, and TRR analyzer issues this refresh command when the victims are not refreshed for the half of T. This is basically ensure that is to ensure that a victim row retain its data correctly until it's potentially refreshed by the TRR-induced refresh, and also it can also correctly remains its data after refreshed and until the TRR analyzer reads data. To analyze how accessing an aggressor row affects the row that TRR detects as aggressive, the analyzer activates and precharges the aggressor rows by hammering an aggressor row with an individual hammer count. And the analyzer can understand how hammers affect the decision of the TRR about on which rows to refresh, basically. And along with the aggressor rows, the analyzer can also use some dummy rows to analyze how to make the aggressor rows undetected by TRR. A dummy row is simply a randomly selected row in the same bank that is not an aggressor or a victim row. The analyzer provides various configuration parameters to study various access patterns. Overall, the TRR analyzer user understands how a certain TRR mechanism operates based on when the TRR mechanism refreshes which of the retention profile rows. So let's look at some of the observations and our newly crafted RowHammer access pattern that bypass the TRR mechanisms. So to implement U-TRR, we used and conducted real DRAM experiments. We used DRAM Bender and FPGA-based DRAM testing infrastructure. We use DRAM Bender because it provides fine-grained control over DRAM commands and timing parameters and temperature. In our study, we studied 15 DDR4 DRAM modules from each of the 3 major DRAM vendors. And in the paper, we have a paper table that provides the detailed information about the test modules. So let's start with the observations we made from the TRR implementation of vendor-A. So vendor-A performs 3 types of TRR. The first one is regular refresh, like every DRAM does. In addition to the regular refresh, vendor-A's TRR mechanism can perform 2 types of TRR-capable refreshes. We refer to them as TRF1 and TRF2. So in this timeline, each tick represents a refresh command that the memory controller issues periodically. And during the first 8 refresh, the DRAM chip performs regular refresh operations. And on the 9th chip, the TRR mechanisms performs TRF1. The next 8 chips, the next 8 refresh commands performs regular refreshes, and the 18th refresh command performs TRF2. Overall, the TRR mechanism uses every 9th refresh command to perform TRF1 and TRF2 in an interlinked manner. Let's look at how TRF1 and TRF2 works. We suspect that the TRR implements a counter table to keep track of repeatedly activated rows, potentially aggressor rows. The table has 16 entries where each entry contains a row address and a counter value to indicate the accumulated memory count of the corresponding row. So when performing TRF1, the TRR mechanism refreshes the neighbor rows, potential victim rows of the row ID that corresponds to the largest value in the table. So we took the largest counter value from the table. On the other hand, TRF2 uses a pointer that indicates the row ID from the table to refresh its potential victim rows. After performing TRF2, the TRF2 pointer advances to the next entry in the table in a circular manner. Based on these observations, we craft a new RowHammer access pattern that circumvents the TRR mechanism of vendor A. So our approach is crafting a RowHammer access pattern is to aim for having the attacked aggressor row discarded from the counter table before the DRAM refresh command. With this, our goal is that the TRF1 and TRF2 to pick any row from the counter table which only consists of dummy activation dummy rows. So for this, we craft the following access pattern. Immediately after a refresh command, we hammer two rows A1 and A2 that are one row apart from each other to perform a double-sided RowHammer attack. And we hammer them. We hammer each of them n times. After that, to discard A1 and A2 from the counter table, we hammer 16 different dummy rows n plus 1 times each. So by hammering the dummy rows more than the aggressor rows, A1 and A2, we make the TRR replace A1 and A2 in the counter table with the dummy rows. So doing so, we basically prevent the TRR mechanism from detecting aggressor row, since both TRF1 and TRF2 can detect a row from the counter table, and the counter table contains only dummy rows. The important thing is here to execute this RowHammer access pattern. It's important to synchronize accesses with the refresh command to perform aggressor and dummy RowHammers at the right time. So we conclude that one can bypass vendor's TRR mechanism by discarding the actual aggressor rows from the counter table by using dummy rows. Let's look at the vendor's B TRR implementation. Differently from vendor A, vendor B has only one type of TRR capable refresh, and we observe that it uses fourth refresh commands. We observe that a TRR capable refresh happens on every fourth refresh command. So we make two key observations regarding how the TRR mechanism of vendor B operates. So first, TRR probabilistically samples the address of an activated row as a potential aggressor row. And second, a newly sampled row overrides the previously sampled row, even if the previous sampled row didn't get a TRR capable refresh, basically. So basically, a TRR capable refresh command targets the row address that has been last sampled by the TRR mechanism. So to circumvent the TRR mechanism of vendor B, our approach is to maximize the probability of having a sampled dummy row by hammering a dummy row as many times as possible before the next TRR capable refresh. So after a TRR capable refresh, we start hammering aggressor row A1 and A2 to perform double-sided hammering. After we hammer DRAM row many times in order to get the TRR mechanism, sample another row activation, these dummy activations, and overrides the previous sample, which potentially includes one of the rows A1 or A1 and A2. As we hammer the dummy rows more, we basically increase the probability of having the dummy row sampled and detected by the following TRR capable refresh. So to conclude, one can circumvent vendor's B's TRR implementation by overwriting a sampled aggressor row by making the TRR mechanism sample a dummy row before the TRR capable refresh operation. Now let's look at our results of our new access patterns. So leveraging these observations, we crafted new RowHammer access patterns that circumvent the TRR of three major DRAM vendors. And to evaluate the effectiveness of these patterns, we performed real DRAM chips on 45 DDR4 DRAM modules, and we observed that new access patterns can cause a large number of RowHammer bit flips. Let's look at the effectiveness of our patterns in a DRAM row granularity. So this plot shows for each of the 45 modules we test, the fraction of rows that experience at least one RowHammer bit flip compared to all rows in a bad DRAM bank. First, as we can see, all 45 modules we tested are vulnerable to our new RowHammer access patterns. And in 20 of the modules, our RowHammer access patterns cause bit flips in almost all of the rows. But why some modules are less vulnerable? We find that it is because of three main reasons. So first, these some modules are basically fundamentally less vulnerable to RowHammer, meaning that the rows in those modules can tolerate a higher number of hammers, and they require a higher number of activations before experiencing a RowHammer bit flip. Second, some modules implement a different TRR mechanism that our custom patterns are not as effective. And we believe that by understanding more of those different TRR mechanisms, we can craft a more effective RowHammer access pattern. And finally, some modules of the vendor scene implements a unique row organization that appears to mitigate the RowHammer at the DRAM circuit level. And we conclude that although some modules are less vulnerable, our access pattern successfully circumvents the TRR implementation of all three major DRAM vendors. So what about ECC? Can ECC protect against our access patterns? The short answer is no. ECC implemented in modern systems can have works on data chunks, and we use 8-byte data chunks. And the ECC can correct 1-bit errors in a data chunk, and ECCs can detect 2-bit errors, but cannot correct or detect 3 or more bit errors. And this plot shows individual for each vendor the distribution of 8-byte data chunks that have 1 to 7 bit RowHammer bit flips. As we can see, the majority of the data chunks are those that have only a single RowHammer bit flip, which can be corrected using a typical ECC. However, our RowHammer access pattern can cause at least 3-bit flips in modules of all three vendors, and further we see up to 7-bit flips in many data words, which the ECC cannot correct or detect. And we conclude that the conventional DRAM ECC cannot protect against our new RowHammer patterns. In the paper, we have more observations regarding how the TRR mechanism of the three vendors operates, and a detailed description of our RowHammer, our newly crafted access patterns and their sensitivity analysis, and also some more observations and results for individual modules. So let me quickly conclude my talk with a quick summary. The RowHammer vulnerability of modern DRAM is the critical reliability and security threat, and DRAM vendors implement target row refresh in their DRAM chips. TRR is an obscure, undocumented, and proprietary RowHammer mitigation mechanism technique. And due to their proprietary nature, the security guarantees of these TRR mechanisms cannot be easily studied. And in this work, we tried to answer these questions. Is TRR fully secure? How can we validate these security guarantees? And for this purpose, we proposed U-TRR, a new methodology that leverages state retention failures to uncover the inner workings of TRR and study its security. So through these analyses, we make several observations. Using U-TRR, we tested 15 modules from each of the three major DRAM vendors. And through this analysis, we make several observations about the TRR mechanisms they implement. And using the observations, we crafted new RowHammer access patterns. And our result shows that first, all 45 modules we tested are vulnerable to our new RowHammer access patterns. Second, our access pattern can cause at least 1-bit flip in almost all rows in many modules. And third, we observed up to 7-bit RowHammer bit flips in an 8-byte data word, making ECC ineffective. And we conclude that TRR does not provide security against RowHammer, since one can easily uncover and craft an access pattern that will bypass a certain TRR mechanism. And we hope that U-TRR can facilitate the development of new RowHammer attacks and more secure RowHammer protection mechanisms. in the future. So thanks for your time. If you have any questions, please feel free to ask. I guess there is no question.
Yeah, no questions for me about your presentation. I just wanted to ask you if maybe you have time just after this to do a quick meeting for my project.
Yeah, sure. Let me first finish the YouTube live stream.
Yeah.